and I'm a lecturer in the astrophysics group. So the astrophysics group has about 40 people in it, and if you come and study here, you'll encounter me probably first in the second year, because I'm in charge of the teaching telescope, which is on the roof of physics. So you'll see that as you go around on your tours. And I also teach the third years about galaxies, or at least I will be teaching the third years this year. So what I want to tell you is give you is a tour of what we do in the astrophysics group, where we focus our attentions on star formation, planet formation, and the properties of planets outside of the solar system. So let me start at the beginning of the story, which is, how do stars form? A seemingly simple question, and of course we know the main answer to this. What is the main force that's pulling material together in the interstellar medium to form stars? Can anyone tell me? Yes? Exactly, gravity. So gravity's pulling. What we're seeing here is a model, a simulation of star formation. What we've done is taken a simulation of the physics of gas, and we're running that inside the supercomputer, or my colleague Professor Bate is running that inside the supercomputer. We're seeing that gas come together under gravity, and it's forming stars in the process. There's some forces that are opposing that gravity as well, so it's quite a complex, turbulent situation, as you can see from the way in which those stars are forming. This is one way in which astrophysicists work. They create theoretical models of what might be going on out there in space. And the other thing that we do is we carry out observations. What is actually going on, what is really happening out there in space. And of course we do that using telescopes. In my case, I'm observing using this telescope, which might look like a large satellite dish. That's because it's working at longer wavelengths, so millimeter wavelengths. And what we're observing with telescopes such as these is the actual gas and dust in space as it's coming together to form stars. So in this image here, you can see a real star-forming region. We can see the filaments of gas, the clumps that we saw at the end of the simulation there. So we can test the models, which are useful because they have the component physics in them, against the observations, which are useful because they tell you how it really is. The models, of course, might not have the right bits of physics in, and certainly they don't have all of the physics in that we might need in order to understand what's going on. So we can work out from the comparison between the two what we might need to change. Do we need to increase the magnetic field, for example? Have we got the temperature in our star formation region just right? So if we look at more detail of what's going on in a small number of those stars as they're forming, the stars here are the intense white cores to these things. That's the ball of gas that's going to go on, and eventually it will start nuclear burning and become a star. But around those protostars, you can see these swirling disks of gas. The gas has some angular momentum as it falls in towards those stars. It spins up, so you end up with the material accreting onto the star through this rotating disk onto the star. In this model, it's a very dynamic process. Those disks form. Some of them form around binaries, pairs of stars. That's quite common. We know many, many stars are in binaries and not just single systems. And some of those disks get disrupted, and some of those stars get thrown out of the star-forming regions in the process. But these disks here are interesting because they are also the places where we know planets form. After all, the planets in our solar system are all arranged in a disk. They're all rotating in the same direction around the sun. What's really nice is, and again this is a model, but we can really start to observe those planet-forming disks around other stars. So we can do that using telescopes such as the Atacama Large Millimeter Array, which is the telescope shown in the bottom picture here. With ALMA, people have made observations such as the one on the left of the disk around the young star HL Tauri. And what you can see is that disk is not a continuous distribution of gas. In fact, it has gaps in that distribution. And those gaps we know from models such as this one by Ben Aliff and Matthew Cate come about because there are planets forming in the disk. So the gaps in the disk, although we're not seeing the planets directly in these observations, they are a strong indicator that there's actually planet formation going on in those protostellar disks. So we can not only see now the stars forming, but we could also look at the process of the planet forming. And to give you some idea of scale, this disk here is just a bit bigger than than the orbit of Neptune in our solar system. We also, in our group, study the properties of planets. So you might know that there are two main ways in which exoplanets, planets outside the solar system, are detected. And the first is through transits. A transit is when you're observing a star, you're tracking its brightness. When a planet passes in front of that star, the brightness of that star dims, and so you have a transit detection. You know that something has happened. If you wait some time until the planet has gone round its orbit, round the back of the star, and comes back in front of the star, then you can have a confirmation of your transit, a second measurement. And now you have two bits of information. You have information on how often the transits occur, which tells you what the period of the orbit is. So that's useful because that contains information about how far away the planet is from its parent star, how massive the planet is. And also you have information on how big the planet is from the amount of light that has dimmed. That tells you the area of the planet compared to the area of the star. So if you detect planets, and here's an example of such a transit event here. This is in fact the first exoplanet that was detected, not in our group but by Charbonneau et al. And you can see that the brightness of the star, which is plotted on the y-axis here, is constant, and then at the time when the planet passes in front, that brightness dips, and it dips by just over 1% in that example. So you have to have quite careful measurements in order to be able to see that difference. And this is quite a large planet. This is a Jupiter-sized planet. So to detect smaller planets, you get a smaller change in the brightness, and you need more sensitive instrumentation to do that. And then you can follow up those measurements with what's called a radial velocity measurement. So a radial velocity measurement is looking at the velocity of the star as the planet goes round it. Because if you remember from gravitation, the star and the planet don't orbit around the center of the star. They orbit around the combined center of mass of the system. So that means that the star is actually orbiting or wobbling about the center of mass of the system, which is slightly offset from the center of that star. And you can measure that velocity shift as it moves forwards and backwards through the Doppler shift. So it moves away from you, it's blue shifted a bit, and towards, away from you, it's red shifted a bit, and towards you, it's blue shifted a bit. So that velocity information gives you additional information, firstly on the period, but it also gives you key information on the orbit of the planet, which allow you to reconstruct then if you know what the mass of the star is, what the mass of the planet is. If you have the planet size from the transit, and you have the planet mass from the radial velocity, then you can plot that and make a comparison to our solar system. So here are our solar system planets, Jupiter, Saturn, Uranus, Neptune, and here's the Earth. And these spots here show the planets that have been characterized so far with both their masses and their radii. Then this is their orbital radius here. The radius of the planet is shown by the size of the planet. You can then go on to look at what the planet might be made of, because if you know its mass and you know its size, you can work out what its density is. So now you can tell whether that planet is made out of gas, or that planet is, like Jupiter, or whether that planet is made out of rock like Earth, or whether it's some composite of the two, as we believe to be the case for several of the planets in our solar system, with a rocky core and then a gaseous outer shell. So we start to model then the interiors of planets and try to understand how those planets are supported, what's going on inside those planets. But even more, we can start to look at what's going on in the atmospheres of planets. And this is something in our group led by David Singh. So when the planet transits in front of the star, the first thing to pass in front of the star is not the solid planet, if there is any solid planet, but it's the outer part of the planet, or its atmosphere. Now, if you look at different wavelengths, that atmosphere transmits or blocks light depending on its constituents, depending on what's in that atmosphere, and it blocks the light at different wavelengths, at different sizes. So if you look at something that's opaque in the atmosphere, the transit is actually slightly deeper and slightly longer than if you look at a wavelength that only detects the core. It's slightly wider and longer because the planet is effectively bigger, it's more opaque over it's opaque over a greater radius if what you're looking at is opaque in the atmosphere. So by looking at a series of different wavelengths and looking at the transits and measuring how big the planet appears to be, you can actually track the composition of the planet. So I've got here, so here's an example of a planet for which David Singh has done this. So on this graph at the bottom here, what we're looking at is wavelength on a log scale. And on this axis here, we're looking at the radius of the planet divided by the radius of the star. So that's the fraction of the light, that's related to the fraction of the light that's been blocked off in the transit. So if more light is blocked off in the transit, the planet is bigger, effectively bigger at that wavelength. That means the atmosphere is opaque further out at that wavelength. And what's been found? Well, the main thing that's been found in this planet, which is quite a hot one, it's about 1,500 Kelvin, is a detection of potassium. So the planet here has got a potassium-filled atmosphere, and that makes it opaque out to larger radii. There are also evidence for clouds in the atmosphere that stop you seeing below a certain radius at any wavelength, and a haze here that as we go towards shorter wavelength, and these are all infrared going into the optical wavelengths. At shorter wavelengths, it becomes more opaque as you go to shorter wavelengths. So at shorter wavelengths, it's more opaque up to higher up in its atmosphere. So not only can we look at the properties of the cores of planets, we can start to look at the properties of the atmospheres of planets. And that's clearly a really new field and something that's got a lot of where there are lots of avenues still to explore. And one of the ways in which we're exploring that is in partnership with the Met Office. So the astrophysics group here have teamed up with people from the Met Office who have very excellent models for the Earth's weather and climate. You can take those models which have all of the necessary atmospheric physics in and translate them to planets outside of the solar system, and use the information that you have from transits, for example, to start to model the weather on other planets. So this is a very new project, and obviously we're not able to forecast weather for individual locations on that planet, but we can get a global idea of what sort of winds you might find on the planets, what sort of temperatures, is the night side hotter than the day side, these kinds of things that we can model with these atmospheres. Where is this going? Well, one of the things, of course, we're interested in is finding another planet that's like the Earth, And there are some candidates out there now that are not much larger than the Earth and sit around stars that are like the Sun and are in what's called the habitable zone, i.e. the zone around those stars where liquid water could exist. And those candidates are only going to increase because there are satellites coming online which are designed specifically to detect those Earth-like planets. So the work on exoplanet atmospheres is likely to develop from modelling atmospheres of hot Jupiter-like planets to modelling atmospheres of rocky terrestrial type planets, which could be like the Earth. And looking for then, of course, looking for signs of life like balance between carbon dioxide and water in the atmosphere. So, in summary, we're the only group that covers all of these activities from star formation through to planet formation, and that produces a good dialogue between people in the group. And we have a good mix of observations and theory, and the exoplanet area is really new and certainly an area where there's plenty of space for growth. How do undergraduates get involved in this? Well, firstly, we'll teach you about many of the aspects of astrophysics through our own research. For example, in observing the universe in the second year, we'll be talking about how you use telescopes to understand what's out there in space, and many of the examples will come from things that we've actually done in the group. One of our fourth-year master's projects is on exoplanets and their atmospheres, and that draws very much on the research that's going on in the group. And if you're here for if you're applying for the bachelor's degree, one of the opportunities to get involved in is working with the telescope in the either with the optical telescope or the radio telescope on the roof and developing that as a project. And if you're here for the master's degree, then many of the areas of research that I've shown you would be available as projects. For example, you might be developing using supercomputer simulations to explore some aspect of star or planet formation. Or you might be using observations from the Atacama Large Millimeter Array or other telescopes in order to study some aspect of star formation. So it's very much something that everybody can get